Hey Tim, check out this section on polynomials. It looks quite interesting. Remember, we used polynomials already. Degree 0 would be just a number like 4. Degree 1, that's our old friend, the straight line, y equals mx plus c. And then degree 2, our quadratic polynomial, y equals ax squared plus bx plus c. We've used that a lot, finding roots, etc. Then you get a cubic one, which is degree 3, quartic, degree 4, and so it goes. So in the general sense, a polynomial is defined as a coefficient, a constant, times a variable to the power n. From there, it goes down to the next coefficient, same variable, to the n minus 1. So we count down all the way to x to the 1, and then finally x to the 0. So it can go down to a constant. So one of the important things with a polynomial is that n is a non-negative integer. So it's got to be 0 or positive. In this degree 0 one, n is actually 0. So it's 4 times x to the 0. So we need to remember that. So there you have a little example here. It looks like a polynomial, but actually it's not. Why? Because it's x to the minus 1, and that's not allowed. Another tip with polynomials is you must write them in descending order. It's just good practice, and it also reduces errors. So, what do we do with polynomials? Well, we can add, subtract, and multiply them. So, for addition and subtraction, here's a little example. A cubic polynomial and added with another cubic polynomial. You can see here on the second one, it hasn't got an x squared term. That's fine. It just means the coefficient is 0. And when we add them, it's adding the 2 plus 1 gives you the 3x to the cube. Then we get a 4 plus 0, because there's no x squared, remains 4x squared. 3 plus 2, 5, and 4 plus 5 is 9. So adding and subtracting is done in much the same way. It's pretty straightforward. Then we get multiplication. If you multiply two polynomials, these two here, the key is to multiply out every term with every other term. And it's most important that, although it sounds simple, it can lead to errors quite easily. So one must be very methodical in how you multiply them. So the first term, you take the first term first, multiply it by each of the other terms, and then take the second term and multiply that out with each of the other terms. And if there's a third term or fourth term, so it goes. And there you have all the terms written out, which can now be easily added together. So here we have the 8x to the 4. He stands alone, so there's nothing to add. He remains as he is. Then 4x to the 3 plus 12x to the 3. And so you pick out the terms in descending order, and that's the final answer. So each term is multiplied by every other term, and keep a strict sequence to avoid errors. It's really unnecessary to make an error at this stage of your sum, because often the multiplication of polynomials is just the start of a more complex example. Now, when we work with polynomials, we use identities. Okay. For example, here's an expression 1 minus x times 1 plus x squared. If one were to times this out, you get 1 plus x squared, and then minus x squared, and minus x to the 3. And you can see that these two terms, the x squareds, actually cancel out, as does the minus x and plus x, and we're left with 1 minus x to the 3. So 1 minus x to the 3 equals this polynomial expression here. Now this is called an identity, because the two sides of the equation are the same for all values of x. It's not as if we solved the equation and found a value of x. These are identical. They mean the same thing for all values of x. And here's another example. Okay. Let's say we were asked to find a, b, c, and r in an expression with a polynomial on the left and an identity 2x minus 1 times ax squared plus bx plus c plus r. Okay, because this has to work for all values of x, we can equate the coefficients of each of the x terms. So if we look at the coefficient of the x to the 3, on the left hand side we've got 2, on the right hand side the x3 coefficient is made up of 2 times a, so it's 2a. Therefore a equals 1. If we look at the coefficient of the x squared, on the left hand side there's 1, and on the right hand side it's made up of 2b and minus a. But we already worked out a, so we can use that to find b is also equal to 1. And so it goes. Our x coefficient is minus 3 on the left hand side, and it's made up of 2c and minus b. And then again we can find c is minus 1. And then very importantly, when we're looking for the constant term, I call it the c term, on the left hand side we've got 4. This is made up of minus 1 times c minus c, and don't forget there's r that hasn't been included in the multiplication of the two polynomials, and r is 3. So it's quite easily done, but the key is to work methodically. Start with your highest order power, work down carefully, and even write here x to the 3 x squared, so it's clear in your mind which one you're working with, and don't miss out any terms. So at the beginning I didn't mention that with polynomials you can also do division. I just thought, whoa, we don't want to do an overload here. But the truth of it is, division by polynomials is no different to using multiplication. I'd like to give an example. Here's a polynomial of 23 divided by 6. Okay, 23 is a polynomial, 6 is a polynomial. Now we can quickly see if we do long division, although it's not done these days, I know you guys have got calculators, but 23 divided by 6 gives you 3 with a remainder 5. Or we could write this as 23 equals 6 times 3 plus 5. So in a polynomial sense, this is how division would be represented. You could have a polynomial, a of x equals b of x, the divisor. Okay, important to remember what you're dividing by. 6 was our divisor there, and b is our divisor here. So it's the divisor times the quotient. Now what is a quotient? Well, quotient is actually the answer. So that's the number 3 that we had in our division sum. So the quotient comes from quote. You know, if you have to ask someone to paint your house, he'll give you an answer. He'll give you a quote. And that's how you remember. It's a quotient, that's the answer. It's important to remember these terms because in the exam you might be asked to find the quotient, or what is a divisor, or that type of thing, or be asked to use it. And then finally there's a remainder. Now the remainder is not necessarily, it's typically not just a number, it's a remainder in terms of x. So each of these are polynomial functions. You can see how the polynomial is built up by multiplying the divisor by the quotient, and that's what division amounts to. So let's do a little example. Here's a 5th degree polynomial, x to the 5, okay, degree 5, and let's say is equal to a divisor. We want to divide him by 2x squared plus 1 times some other quotient, some other answer, plus the remainder. Now this is very important. You need to look at what is my degree of my quotient going to be. So the degree of my polynomial was 5, the degree of my divisor was 2. So the degree of my quotient is 5 minus 2 equals 3. You can quickly see that if you had a 2 degree polynomial times a 3 degree, you'll get a 5 degree. So the quotient is always the difference between these two. Okay, what about the remainder? Let's look at our little example here with numbers. You can see that the remainder in this case was 5, which is 1 less than 6, the divisor. And that's exactly how all polynomials apply. You'll see that the degree of the remainder is always 1 less than the divisor. So in this case, my r of x would be a first order degree. Okay, so that's 2 minus 1 gives you the 1. So it's always 1 less is the maximum that the remainder will be. Okay, now that's very useful because if we know the degree of my q of x and the degree of my r of x, we can quickly see how many variables we need to represent it and find those coefficients. Here's a proper full example. So we've got a cubic polynomial, and we want to divide him by x minus 2. Okay, so 2x to the 3 plus 4x minus 1 equals x minus 2, the divisor, times some quadratic. Now because this was a degree 3, this is a degree 1, my quotient is going to be 3 minus 1 is 2. And my remainder is going to be 1 less than a power of 1. So my remainder is the 0 power, the 0 degree polynomial. So he's got no x's in him. It's just a constant. So if we equate the coefficients, similar to the previous example we did, on the left hand side the coefficient of the x3 term is 2, and on the right hand side it's simply a. You can see there it's derived from the x times the ax squared. That's a. So a equals 2. From there we can look here on the left hand side, our coefficient of x squared is 0. There isn't an x squared term, so we say 0 equals, and the x squared term is made up here of b and minus 2a. Since we worked out a, we can find b equals 4. And so it goes. We can look at the coefficient of the x term, which is 4. We can equate it to the coefficient, the x term is derived from x times c, which is c, and minus 2 times b. Since we know b already, we can work out c. And finally, the constant term on the left is minus 1, and the constant term on the right is derived from minus 2 times c, and don't forget plus r. And so we find r equals 23. Okay, then we can move on to the remainder theorem. So polynomials questions generally are divided into two categories. One is working out the division of a polynomial, which can get quite complex, but if you stick to the rules, they're fairly simple, and that's what we've just covered here. But now there's a special case. Okay, for a polynomial that's divided by a linear polynomial. So my polynomial, the divisor is a linear one, and we write them in the form as sx minus t. Then the remainder is equal to polynomial of t over s. So you put x equals t over s into your polynomial, and that will give you your remainder. So let's look at a proof for that. So the polynomial p of x equals the divisor times some quotient plus a remainder. Okay, you can see my remainder is the order 1 less than my divisor, so my remainder is just a number. There's no x terms. So now, if we were to insert x equals t over s into my polynomial and into sx minus t, okay, we don't know what our quotient is, so we can't insert it there. You can quickly see that if you insert t over s into this sx minus t, you get 0. That means this whole term here bombs out, it's 0. And so p of t over s is equal to r. So this is something that you need to always be on the lookout for. If you're asked to divide a polynomial by a linear polynomial, i.e. sx minus t, then you must read the question carefully and find out, do they actually want to know what the quotient is, or they're only asking you to find the remainder. And you'll see also that the marks will be a lot less because it's so easy. You just put in t over s into your polynomial, and away you go. You'll find r immediately. And this leads us to the factor theorem. Now in our example of just normal division, if I say 24 divided by 6, I get 4, remainder 0. We all know that 4 is a factor. 6 is a factor of 24. It's a number that divides completely into 24. And this applies to polynomials as well, to more complex polynomials as well. So the rule says that if a divisor, sx minus t, is a factor of p of x, then p of t over s equals 0. Now that makes sense because if we say p of x equals the divisor, sx minus t, times some quotient plus r, we already know that r equals 0 because we've said that sx minus t is a factor. We've already said that it's a factor, so there's no remainder. So let's just do an example now. So we're going to try and factorize p of x equals 3x squared, x to the 3 plus 4x squared plus 5x minus 6. You can see this is a lot more complex than what we've done. I think we've only done up to quadratics. So we're going to say that p of x equals some factor sx minus t times q of x plus 0. We can just ignore that from now on. So p of x equals sx minus t times, and guess what? The quotient is going to be a quadratic because the p of x is a degree 3, the divisor is degree 1, so your quadratic is degree 2. So we can write this quadratic as ax squared plus bx plus c. So the first step is we're going to try some different values for s and for t. It's a bit of a trial and error. Okay, so the first trick is to only choose positive values for s. Now why is that? If s is negative and it gives another t, you can just times the whole thing by -1 and swap them both. So you only need to pick s as positive and the t will follow. And then a and b, it'll affect the values of a, b, and c. Their polarity will just reverse. Okay, so number one, you choose s as positive always. In our case, because we have the coefficient of x to the 3, this is made up of s times a. So s would have to be either 1 or 3. So if s is 1, a would be 3. If s is 3, a would be 1. So s can be 1 or 3, positive. Okay. Then if we look at t, t and c form the constant term. And in our case, minus t times c must equal -6. So that means that t can be plus or minus 1, in which case c would be plus or minus 6. T could be plus or minus 2, in which case c would be plus or minus 3. T could be plus or minus 3 or plus or minus 6. Ouch. Now that's a lot of options. But let's look at it a bit more closely. First of all, let's write down all the combinations. So, s we said could be 1 or 3. So let's do two columns here. S is 1, s is 3. T is 1 minus 1, 2 minus 2, 3 minus 3, and 6 minus 6. That's a lot of combinations to try. And similarly, when s is 3, we've got all these combinations of t. But one must just be very careful here. We don't have too many options. If you look at our original polynomial, there are no terms here that are common. So you can't take out a common factor. It's not like they all divide by 3 or all divide by 2. So look carefully for that. You can see here, it's in its simplest form. There's no common factor taken there. Therefore, you can't have s and t as both dividing by 3, for example. Okay, you can't. So 3 is not an option. 3 minus 3 is not an option. 3 6 is not an option, and 3 minus 6 is not an option. So I've just scratched those out. So that's the next step. You eliminate any common factors. Look at all your possibilities, eliminate the common factors. Now try p of t over s for the different pairs. So you could try t is 1, s is 1, so 1 over 1 is 1. So p of 1, and you test it out and see. When you get one of these pairs that works out that p of t over s equals 0, then you've found a factor. And then it's easy to find the next factor because the next factor is just a quadratic. So we can quickly solve that using our normal method of inspection or whichever approach we want to adopt there. Okay, so I'd like to do an example on the factor theorem. If we've got a polynomial that's a cubic polynomial like this, then we write p of x equals sx minus t times some q of x. Notice that I've left out the remainder because we've already said because it's a factor there's no remainder. And we can look at this and we know that p of x is a third degree, the divisor is a first degree, so my quotient is going to be a second degree. And we can write him as ax squared plus bx plus c. Now if we look at picking different values of s, we can see that the s times a will give you the 6, the coefficient of the cubic. So s can be either 1, 2, 3, and 6, which are all factors of 6. Similarly, t times c, minus t times c, will give you the minus 2. So t can be plus or minus 1 or plus or minus 2. So now we've got a lot of combinations we can write down. And there we have them all. Okay, so s is 1, 2, 3, 6, and t can be plus or minus 1, plus or minus 2, etc. Now again we can see that with this polynomial there were no common factors. Okay, there's no common numbers that these guys can divide by. So we can't have 2, 2 or 2 minus 2, so we can eliminate those. 6, 2 or 6 minus 2 because these guys can both divide by 2. So we haven't got any common factors in our polynomial. So we can take off that first pair and we can try it out. And we can see, right, let's put s equals 1, and t equals 1 into our polynomial. So p of 1 over 1, so t over s equals p of 1, which is equal to 6 times 1 cubed plus 7 times 1 squared minus 1 minus 2. You can see there we're just putting it straight into that. We're putting 1 into that polynomial. And we find that it's 10. But there's just a tip here. You don't need to work out each pair. Once you know that it's not 0, you can see very quickly with the eye that 6 plus 7 is minus 1 minus 2 is not going to be 0. So you can just move on to the next pair. So it becomes quite quick to test these. Then we can go on to our next pair where with s is 1 and t is minus 1. So p of minus 1 equals 6 times minus 1 cubed plus 7 times minus 1 squared, etc. And then we find out that it's 0. So we found our first factor. So hence, sx minus t is a factor. So 1x minus minus 1 is a factor, and x plus 1 is a factor. So even though t was minus 1, our factor is x plus 1. Just be careful with the signage here. So what's the next step? Now we have our polynomial. We have our polynomial. It's equal to a factor times ax squared plus bx plus c. Now I've cheated a little bit because I've looked at this and said, right, my cubic is 6. The coefficient of the cubic is 6, and that's derived from 1x times something x squared. So immediately I know that a is 6, okay? Because you can see there I'm getting my 6. Similarly, I can find my c term because it's minus 2, and I know that this is 1, so 1 times c gives you minus 2. So I can quickly write that in, and I don't need to waste a line doing that. But b, I don't know what b is, so I've just kept him as b. And to get b, I choose the x squared term, the coefficient of the x squared term. On the left hand side it's 7, and on the right hand side it's derived from x times bx, so it's b and 1 times 6, which is 6, so b is equal to 1. So now I'm well on my way towards factorizing this polynomial. I've got an x plus 1 times 6x squared plus x minus 2. To factorize further, I can do it by inspection, and I can see that this quadratic can be factorized as 2x minus 1 times 3x plus 2. And notice I made a little mistake there on the way, which just shows how easy it is to make mistakes and how one must just work carefully. And finally, my p of x equals x plus 1 times 2x minus 1 times 3x plus 2. There are 3 factors there. So that's all we have on polynomials. Thank you so much for listening, and you're welcome to contact me by email if you want any examples answered or you have any questions. I'll be more than happy to help. Thanks very much. Ciao.